Thanks for making time to watch this video. This video will walk you through our Blackboard activity Polar Puzzle. This is an activity in creating probability tree diagrams. And this is an important skill that'll come up again on our quiz and in other places. So if you do have any trouble at all making a tree diagram and making a connection between the tree diagram and the fundamental counting principle and probability, then I hope that this video will help you. Here's what our activity looks like, and notice that there are two puzzles, the top two riddles. If you do feel inclined to complete those puzzles, the benefit is that it'll check your answers for you. Because if you don't solve the puzzle, or let me back up and say, if you don't get the right answers for the questions, then the puzzle is going to come up with gibberish and you won't get a solution to that puzzle. And then you'll know something must be wrong in one of your answers. However, if you end up getting a sensible answer to the very corny jokes here, the very corny riddles, then you'll know that your answers to these 10 questions are probably correct. Let's start with number 1. If you spin each of these spinners once, how many possible outcomes are there? I've created a tree diagram, and you can see this tree diagram in our section, in section 11.4. And notice that the first spinner has an A, B, and C. Let me turn on a highlighter here so I can show you. Our first spinner has the A, B, and C. So the first branch of our tree diagram goes to A, B, and C. After we spin an A, the second spinner could land on any number 1 through 5. So after the first spinner lands on A, we might get a 1, a 2, a 3, a 4, or a 5. And then same thing for the B. After we spin a B, it could be 1, 2, 3, 4, 5. After you spin a C, 1, 2, 3, 4, 5. Now this diagram is called a tree diagram. After you create the tree, you should be able to list all the sample points in the sample space. After you've created the tree diagram, we could say that A1, A2, A3, A4, and A5 are all elements of the sample space, or in other words, those are all sample points. B1, B2, B3, B4, and B5 are the next 5 elements in the sample space. And then, of course, we have the C1, C2, C3, C4, and C5. All together, you could see that there are 15 outcomes. But let's look at one other way at how to find that. It is important to be able to do this tree diagram, but because there are only 2 steps to this problem, we could also make a cross chart. Here's how that would look. In the rows, we have the A, B, and C. That was our first spinner. In the columns, we have 1, 2, 3, 4, and 5. That was our second spinner. And so this element is an A1 and so on, right? Do you see this, like the cross between the B and the 4 is this element in the sample space B4 and so on. So that's one other way that you could get a list of the sample points that make up the sample space. This only works as kind of a chart because it's 2-dimensional. This kind of chart can only work if there were only 2 different steps. So in this case, there were 2 spinners. This works. You'd have to have a cube if there were 3 different steps. So it's not really worth the same process of making that chart. Doesn't really work when there's more than 2 possibilities. Now, another approach to this question is using the fundamental counting principle. For the fundamental counting principle, if the first experiment has m distinct outcomes, so in this case, spinner 1 has a grand total of 3 possible outcomes, right? And the second experiment has n distinct outcomes, so our spinner 2 has 5 outcomes. Then the 2 experiments in that specific order have m times n, or in this case 3 times 5, 15 outcomes. Notice that's what we got in our tree diagram also. Now let me be clear about this activity. One approach is just to jump to the answer and say, okay, it's easily 3 times 5. And that's okay in some cases. But I do want to highlight the importance of being able to create the tree diagram as well. Even though the tree diagram isn't the most efficient way of doing every problem, being able to make the tree diagram is going to be important. So we see that there were 15 outcomes. Let's go to a question on the second part of this activity. What's the probability that if we selected one of these different items from the sample space, that it's got an A and a number less than 4? Well, one way to answer this question is to make the tree diagram, list the sample points in the sample space, and then look at how many favorable outcomes are there. That's 3, an A1, an A2, and an A3. I'll have an A and a number less than 4. So the number of favorable outcomes is 3. Out of our total number of outcomes was 3 times 5, or 15. So the probability, if someone just spinned these spinners, and let's say that you win $100 if you get an A and a number that's less than 4. That would be these 3 A's, right? An A and a 1, 2, or a 3. We could solve that probability problem by counting from the sample space how many favorable outcomes there are. There's 3 of them, 1, 2, 3. Out of the total number of elements in the sample space, that's everything, that was 15. And if we want to change this to a percent, we'd first change it to a decimal, 3 divided by 15. And the directions say that when necessary, round to 4 decimal places. This one doesn't need to be rounded because it terminates at 2/10. But then we need to be able to write that as a percent, multiply by 100 to get 20%. Let's go on to question S. If you spin each of these spinners once, how many possible outcomes are there? How about the probability of getting an A or a B and a number less than 5? Do you see that because we already have the sample space listed, we could do this problem quite easily by using that sample space. How many of the elements, the sample points, have an A or a B? That's 10. But also, and a number less than 5. So that's a 1, 2, 3, 4. That's these 4 and these 4 for a total of 8. Out of all the possible outcomes, 15. If I divide 8 divided by 15, I get 0.5333, and that 3 keeps repeating. When I round it to 4 decimal places, I'd stop at the 3. If I change that to a percent, I'm going to multiply by 100, or simply move that decimal 2 places to the right to get 53 and 33 hundredths percent, 53.33%. We could answer another probability question. What's the probability of getting an outcome that has an A and not a 4? It looks like there's 1, 2, 3, 4 of those out of the total 15. 4 divided by 15, 0.26 repeating. If I round to 4 decimal places, because the next digit after that was a 6, we round up to 7. So we get 0.2667. And then if I multiply by 100, I get 26.67%, or 26 and 67 hundredths percent. Let's look at the next scenario. Scenario S. Zoo officials are trying to decide on a name for their new baby polar bear. The first name is going to be Bubby, Cubby, Snowball, Alabaster, or Alabaster. 4 different choices for the first name. And his middle name is going to be Frosty, Flake, or Freeze. How many different choices are there? We could do this with a fundamental counting principle, and that's by far the quickest, most efficient method. But that's also, just use this as a practice for how to create a tree diagram. To create the tree diagram, I'm going to start with the first name. We could have a Buddy, Cubby, Snowball, or Alabaster. Once we select this Buddy as the first name, the second name could be Frosty, Flake, or Freeze. So I get Buddy Frosty, Buddy Flake, Buddy Freeze. I hope they don't choose any of those names. And then the first name, once we choose it as Cubby, and then choose the second name, we could get Cubby Frosty, Cubby Flake, Cubby Freeze. Once we choose Snowball as a first name, we could then choose Frosty, Flake, or Freeze. So Snowball Frosty, Snowball Flake, or Snowball Freeze. And then finally, if Alabaster is the first name, his or her name could be Alabaster Frosty, Alabaster Flake, Alabaster Freeze. Do you see how many there are total? If we count them, 3, 6, 9, 12. It looks like there are a grand total of 12. So how many different choices do they have? 12 different choices altogether. But here we can see it being done with the tree diagram. If you wanted to use that chart, we could, because there are only 2 choices, a first name and a second name, we could do this in the chart where in the rows I'm going to put Buddy, Cubby, Snowball, and Alabaster. And then in the columns, we've got Frosty, Flake, and Freeze. So we could get each of those first names combined with each of those middle names gives us a total of 12. And then if I wanted to answer this question, what's the probability that you have a U, a letter U, in the name? Well, I can look at the sample space, and I'm going to select every name that has a U. That's Buddy Frosty, Buddy Flake, Buddy Freeze, Cubby Frosty, Cubby Flake, Cubby Freeze. Those are the only ones with the letter U. Oops, sorry, I didn't mean to scribble it out. I meant to highlight it. So those are all the examples that have a letter U. And it looks like there is a grand total of 6 of them. 6 out of 12 is 50%. What's the probability of getting a U and ending with E? If I consult the sample space, it looks like there are 4 options that are both a U and end with an E. So 4 out of 12 gives us 33%. And then here's an interesting question. What's the probability that his name is Frosty Flake? Well, when I look at the sample points, here they all are. When I look at this list of all the possibilities, none of them are Frosty Flake. There are some that have a Frosty or have a Flake. So we could say that that's 67% of the names have either Frosty or Flake. But how many of those names have both Frosty and Flake? So Frosty is a first name, Flake is a second name. This is almost a trick question, isn't it? The probability is going to be 0. It's impossible unless we have someone who breaks the naming rule and they don't choose a first name from this pink list, Buddy, Cubby, Snowball, Alabaster, and they don't choose the second name from the blue list. There's no combination of Frosty together with Flake, though I think that's the best name, if you ask me. But that's a whole different story, right? Let's look at the next question, letter N. Java needs a roll of film for her 35 millimeter antique camera. Based on the information in the table, how many different kinds of film can she buy? Well, I started with a tree diagram, and you can see that the speed I have in pink is either 100, 200, or 400. Next, I add the exposure. So if we chose a speed of 100, then the exposure could be speed of 100, 12 exposures, speed of 100, 24 exposures, speed of 100, 36 exposures. And then after that, I can select either prints or slides. So it looks like a 112 print or a 112 exposures slides. Those are the first two elements in the sample space. Or we could do 124 print, 124 slide, and so on. And when I do this, I end up with the whole list of the sample points. And I have the sample space listed here to the right. You should also be able to do that on your own. Now, because this has 3 steps to it, we're choosing a speed, an exposure, and a type. It doesn't really work to put it in a rectangle because it would have to actually be a cube because we have 3 dimensions. We're choosing a speed, an exposure, and then that third choice, a type. So for this one, it's not going to make sense to have it in a rectangle. So let's instead look at how we could do this problem using the fundamental counting principle. There's 3 ways to choose the speed, 3 ways to choose the number of exposures, and 2 ways to choose the type. So there's a total of 3 times 3 times 2. And the way I do that is I say 3 times 3 is 9, and 9 times 2 is 18. So I hope you're doing it mentally, not pulling out a calculator for this arithmetic. But we get that there's a total of 18 sample points in this sample space. Let's answer a probability question. Here it is in the bottom. What's the probability of having 200 speed film with prints? If we look at all the elements in the sample space, that's the ones that I have highlighted here, 212 exposures, print, 200 speed, 24 exposures, prints, 200 speed, 36 exposures, print. So it looks like there's a grand total of 3 out of the 18. If I divide 3 divided by 18, I get 0.16 repeating. Rounding to 4 decimal places, I'm going to make that last 6 a 7 because it's closer to 7 than it is to 6. And then changing that to a percent, I'm going to multiply by 100 to get 16.67%. Another example, and we're going to not worry with a tree diagram for these examples because they get quite involved and there's so many outcomes that a tree really isn't very sensible at all for these examples. But for making a license plate in Toontown that consists of a total of 4 characters, where the first 3 characters are going to be a letter and the last is going to be a digit from 1 to 9, here's how we'd apply the fundamental counting principle. We'd look at that first letter is going to be, let me change it to a pen, an A, B, C, D, E, and so on up to Z. Now there's a total of 26 letters in our alphabet, so there are 26 letters to choose from. This question doesn't say anything about disallowing a repeat, so when I go to select the second letter, I could use the same letter I used in the first choice again, so I'd get 26 again, and then I'd get the third choice is 26 choices to choose from, and then the digits 1 through 9 there's a total of 9 of those. So it looks like our grand total comes up to 26 times itself 3 times, times 9. And I'm going to leave that calculation to you because it's just putting it in the calculator. And you should find your answer as one of these numbers in the riddle. But that's using the fundamental counting principle. This letter G, we could make a tree diagram, and I'd recommend, oh wait, actually I don't recommend a tree diagram here. Don't make a tree diagram for this one. I apologize for that. I started this problem with a tree diagram, and then I realized, wait a minute, that doesn't make any sense at all. So just that's, if you wouldn't mind just disregarding that page, I apologize for that. I thought I deleted that before I started our video. We're going to look at this just as the fundamental counting principle, and here's how. The first question, there's 5 answers to choose from. The second question has 5 answers to choose from, and the third has 5 answers to choose from. So how many different answer combinations are there? It's going to be 5 cubed. 5 times 5 times 5. That'll tell us how many total possibilities there are. And this is another one that I'd encourage you to try doing mentally, because 25 times 5, just think if you could picture in your hand that you had 5 quarters, 5 25-cent pieces. Are you able to calculate how much money you'd have? You'd have 125 cents, right? So you might be able to do this arithmetic mentally. Go ahead and check it with a calculator if you're more comfortable doing so, but 5 cubed is going to be 125. Let's look at Argyle's outfit selection. He has 10 t-shirts, 7 pairs of shorts, and 2 pairs of shoes. So if I wanted to apply the fundamental counting principle, we'd multiply 10, that's a number of shirts, times 7, that's a number of shorts, times 2, that's the number of shoes. I'm going to do this one mentally also, by the way. Here's how. 7 times 2 is easily 14, right? And you can do 10 times 14 without a calculator, can't you? And that's going to give us our total number of different outfits. Did you find your answer in the puzzle, by the way? What you'll do, let me go back to that. What you'll do, since we get 140, just in case you haven't followed how easy it is to get that bonus with the puzzle, we're going to find this 140 in the puzzle up here, and every time that there's a 140, it looks like there's only the 1. Is that the only 140? Yeah. So that 140, we're going to put the letter A to start solving that puzzle. Let's move on to letter I. Balloons or Bust sells balloons, and we can choose from 18 colors, 3 sizes, and it looks like there's 1, 2, 3, 4, 5, 6 ribbons. So if I multiply 18 times 3 times 6, on my calculator, I'm going to do 18 times 18 because I'm going to do this 3 times 6 mentally, and then put the 18 times 18 in the calculator. Let's look at Camp Cornflake. There's 3 different activity periods, and for period 1, there's 3 choices. For period 2, there's 3 choices, and for period 3, there's 3 choices. So it looks like there's a total of 27 different schedules we could make. How do I get that 27? Well, you could also see this with a tree diagram. The first choice was leather work. Then the second choice could be archery, riflery, or nature study. And then each of those branch off to canoeing, water skiing, and swimming. And when you do that, you'd end up with 27 different schedule choices. Moving on to letter B, the 4-course dinner. The 4-course dinner, it looks like there's 2 choices, soup or salad, and then 9 main courses, and then 4 desserts. And when we choose between, coffee or tea, there's two there. So if I multiply the number of ways we could make each choice, 2 times 9 times 4 times 2, I'm going to simplify this a little bit mentally and do 18 times 8. And that way I'm only putting that one product in the calculator. It cuts down some of the calculating because some of that arithmetic is so easy just mentally, right? Well, let's close up with this last one as a tree diagram to make sure we could review that, how to do a tree diagram one more way. And this is going to be similar to another activity we're going to see in the future called the McDonald's Have It Your Way, Build a Burger. In the future, we're going to come to this activity, Build Your Own Burger at McDonald's, and it's going to be similar to this. And here's why it's similar. For each of these options, the monitor, keyboard, DVD player, and wireless card, you've got either a yes or a no. Yes to the monitor or no to the monitor. Yes to the keyboard or no to the keyboard. Yes to the DVD player or no to the DVD player, or so on. So what we're going to end up doing is saying that each choice has two options. And there's 4 choices, so we multiply that 2 times itself, 2 because there's 2 choices each time we have an option. And then 4 times that we're having to say yes or no. So that's one approach to doing this problem, and that's the approach that the McDonald's Build-A-Burger will take. But you could also see this with the tree diagram, and I hope that you can pause the video and make sure you've got your own tree, because your written work will need to show that tree. But for the tree, you'd see that the first selection is a monitor or no monitor, right? And then keyboard or no keyboard, the DVD, and the wireless card. If I listed each of these, let me just do one of them. A monitor, keyboard, DVD, and wireless. Then that's the one item in the sample space. Instead of writing all of these words each time, what if I do this? I'll say monitor, no keyboard, so I'll just write the K with a slash through it. Oh, actually, let me step back. Sorry, I skipped ahead. We've got, let me highlight it so that we're sure to get all of them. Monitor, keyboard, DVD, wireless. Monitor, keyboard, DVD, no wireless. So that's monitor, keyboard, DVD, and no wireless. So I'll put a slash through the wireless. And now I'm ready to go on to the next one, which is monitor, keyboard, no DVD, and then wireless or no wireless. Here's what those would look like. If I list a monitor, keyboard, no DVD, monitor, keyboard, no DVD, and then either wireless or no wireless, and so on. That would give us the first 4 elements in the sample space. You should be able to list the other 12 as well. And another way to do this problem, as I kind of showed earlier, is with this fundamental counting principle, 2 ways to make a decision about the monitor, 2 ways to decide about the keyboard for the DVD, and for the wireless card. So we get a total of 2 to the 4th power, or 16 options. Well, that's all in the video, but if you do have questions, please don't hesitate to contact me. I'm happy to work with students on these activities and want to make sure you understand each part of it, and I'm here to help you. Thanks for the work you're doing, and I hope that you are successful at uploading your answers on Blackboard and then uploading your written work as well.